help you? Can you just take a video or do you have a pen drive? Because we can save as a backup, and if something happens, we can use this computer. Yeah. If something okay, I already okay. So if something happens, we can save here. Yeah. Perfect. If you want, we can send a quick charger, but okay, perfect. São dois computadores. O primeiro é esse. Ok. Fazer uma apresentação desse blog. Aí esse laser point do computador. Do dele. Não, esse é daqui. Isso aqui. Entendi. Deixar pra pertinho também.
mostro as coisas coloridas. Boa tarde a todos. Então, obrigado por estarem aqui. É um seminário do Centro de Inovação e Sistemas Logísticos, que é um NAP aqui da escola. Obrigado. Então, nós vamos fazer hoje um seminário muito interessante. Nós temos aqui o professor Lei Zhao, da Universidade de Tsinghua, que é em Beijing, na China. Então, tem muitas coisas que são muito diferentes do Brasil, mas tem muitas coisas que são muito parecidas com o Brasil, que, inclusive, são coisas interessantes. Tá? Então, vamos fazer aqui uma abertura formal. Meu nome é Hugo Yoshizaki, sou um dos coordenadores do CISLOG, junto com o professor Cláudio Barbieri. Então, vamos fazer uma rápida abertura aqui, para nós podermos iniciar o evento logo em seguida. Ok, gente? Só para vocês saberem, vocês estão sendo gravados e transmitidos ao vivo pela internet. Então, por favor, saibam disso, tá? Muito bem. Então, vou rapidamente compor aqui a mesa, chamando as autoridades presentes. Primeiramente, vou chamar aqui o professor Cláudio Barbieri da Cunha, que atualmente é o chefe do Departamento de Transportes e também um dos coordenadores do CISLOG. Obrigado, Cláudio. E vou também aqui pedir para tomar assento o professor Reinaldo Judice, que é o nosso vice-diretor da Escola Politécnica da Universidade de São Paulo. Por favor, Reinaldo. Eu não vou sentar na mesa porque eu estou chamando os trabalhos, tá, gente? Então, e também é uma pessoa menos para falar na abertura, tá bom? Então, vou pedir aqui para o professor Reinaldo fazer as boas-vindas pela escola e dizer algumas poucas palavras, então. Por favor, Reinaldo.
Inglês ou português?
Hã?
Inglês ou português?
Oi?
Inglês ou português nesse momento?
Pode ser em inglês, porque aí o Lei vai entender o que você está falando.
Okay.
Good
afternoon, everyone. On behalf of Professor Liedi Benucci, the director of Polytechnic School of University of São Paulo, who I am representing in this event, I'd like to express my great pleasure in having you here in this open ceremony, in participating in this open ceremony. I'd like to congratulate Professor Hugo Yoshizaki and Professor Claudio Barbieri, the coordinators of the Center of Innovation and Logistics System, for the organization of this event. I'd like to congratulate Professor Lei Zhao from University Tsinghua University. Did I say it correct? Who gave this talk to you? We who live in a city like São Paulo knows very well the problems of big cities, and of course the topic of this event is quite important for improve our lives in big cities like São Paulo. So I will be very short in my talk. Just wish to talk. To which the talk of Professor Lei Zhao inspire fruitful discussions, and I'd like you enjoy the lecture. Thank you.
Now, Professor Claudio, for the lab, please.
Okay. Good afternoon to everyone. It's a great pleasure to be here. I would like to thank initially Professor Reinaldo, representing our Dean, Professor Liedi, for being here with us in this opening ceremony. And I would like to thank Professor Lei Zhao from Tsinghua University for being here with us here today. We at CISLOG, Center for Innovation in Logistics Systems, and the Departments of Transportation Engineering, which I am the head at the moment, and also the Department of Industry Engineering. I just met the head of the department during lunch. We are very grateful for having you here. Professor Lei Zhao has done his PhD at Arizona State University. He works in retail operations and logistics in megacities. He has co-authored several articles with very prestigious researchers in the areas, among Jean-François, who some of you may have had the chance of watching him here some time ago, and also Professor Warren Powell from Princeton University, Professor Martin Salvosberg from Georgia Tech, and other very prestigious research. So Professor Lei Zhao does top research in fields that tries to apply mathematical models, analytics, to very important and relevant problems in urban distribution, especially in megacities in developing countries. So I hope you enjoy his presentation. I think you are going to enjoy it very much. And I'd like to thank you all for being here, for Hugo for being kind enough to be our host, and Professor Reynaldo for being here, missing part of an important meeting that he should be attending at the moment. And again, Professor Lei Zhao for taking such a long trip coming to Brazil despite all your busy activities in the last few months. Thank you very much.
Com isso a gente pode encerrar a abertura. Queria agradecer aqui então a presença do professor Cláudio e do professor Reinaldo. E obrigado, gente. And now I will make a very short presentation of the Center of Innovation in Logistics Systems because somebody asked me to do that. So this is the center. Thank you. The slides will be in Portuguese because, of course, the audience is Brazilian, but I will talk in English because of Lei, okay? Sorry, I don't speak very good Cantonese or Mandarin, very poor, but it's a very good thing that Lei is here. I have known Lei for 2012, yeah, 7 years now, yeah. And now we're starting a collaboration, formal collaboration, because Professor Daniel Costa, he's also going to China to work with Lei for a short period. So we're going to start some more, closer relationships, okay? So thank you so much for being here, Lei, and Daniel for also being supportive of this kind of initiative, okay? Well, what is the Center for Innovation in Logistics Systems? It belongs to University of São Paulo. I will not tell you what is University of São Paulo because most of you know very well University of São Paulo, one of the largest universities in Brazil. About a third of all scientific research in this country are made here, and so on. Escola Politécnica is one of the engineering schools at USP. We have 17 undergraduate courses, 11 graduate programs. We are founded in 1893, so 125, something like that. We are 15 departments, and probably most of you don't know, we are more than 100 labs. And this means that if you have any technological problem, please come to Escola Politécnica. We'll be very glad to help you with your technological problems, okay? We are almost 500 faculty, 4,500 undergraduate, and 2,500 graduate students. Big engineering school, okay? And we are just part of it. The Center for Innovation in Logistics Systems, we are basically concerned about developing research in order that we could consolidate different knowledges that comes from all these 100 laboratories. So we do a lot of interdisciplinary research here because logistics is quite interdisciplinary too. What we work with? We work mostly with education, research, and outreach. And regarding the education, of course, we work with the undergraduate in undergraduate regarding, for instance, civil engineering, transportation engineering, production engineering, graduate courses for masters and PhD regarding research, because you see, the students here are the guys who work with us to do research. And in this case, we work with sustainable logistics, and under sustainable logistics, two main areas: urban logistics and humanitarian operations, okay? And as we have education and research, we apply this in the outreach using, for instance, our collaboration with partner companies, continuing education, conference and workshops like this one, and of course, studies, projects, and things like that. We are oriented to study and propose solutions to actual problems we have in logistics in Brazil and in the world, okay? We are, of course, it's very important to tell you that we are closely inspired by the Center for Transportation and Logistics at MIT, which are one of our main partners here. This is our team. So me and Claudio, a bunch of researchers. Daniel is here. Some undergraduate students, and Fabiana, who is our administrative staff. We also have the support of a lot of people here at the Escola Politécnica. And for instance, for this event, we have our event people here, for instance, Álvaro, and Cristiane and Fabiana, you saw them at the registration desk. So thank you very much. Well, who are our main partners? So I told you it was the Center for Transportation and Logistics at MIT. We are also part of the Volvo Research and Educational Center of Excellence for Sustainable Urban Freight Systems, which is coordinated by the RPI with Professor José Roguin Veras. We are also working together with Kyoto University and Lugano University mostly with humanitarian operations with Professor Paulo Gonçalves. We also are part of the Transportation Research Board in the U.S. It's part of the National Academy of Sciences of the U.S. We also have a collaboration with the Brazilian Association of Logistics and also with the Production Operations Management Society in the U.S., which I am one of the vice presidents. And we also, to do all this, we need money that comes from these agencies, from CNPq, FAPESP, and CAPES. And also we have the support from our company partners, which are 5 big companies who help us to organize this kind of events. One of them is, I think that most of you know, Ambev, which works with beverage. Somebody from Ambev here? No? Okay. Realiza, Grupo Pão de Açúcar, Bayer, and Sanofi. Okay? So thanks for the company partners who makes this kind of event possible. The SysLog is part of the VRF Center of Excellence for Sustainable Urban Freight Systems. We have a collaboration with a lot of universities around the world. So this is just a small sample of what we are doing today with many colleagues from emerging economies. Okay? One of the projects we have done together with people from the Secretary of Transportation here at City of São Paulo was of our deliveries pilot project that was in 2015. And where is Flavio in the, our friends here from the São Paulo Department of Transportation here. If you want to see more details, you can download this from the web page from the ANTP. And we also have a webinar and the website from the Volvo Center. And now it's talking about what Lei we're going to do. We have a very good friends, which are Edgar Blanco, which now is a chief scientist or whatever about innovation in supply chain management at Amazon. And also Professor Jan Franzo, who left Eindhoven, and now he is the dean of the Kuhne Logistics School in Hamburg. And I have the privilege of working with them, and at the same time that Lei was working with them. And we have they edited a book about small retailers in emerging economies. I think your chapter is the second chapter, chapter 3. Yeah, and ours is the last chapter, Claudio. No, next to last chapter. And so you can find this in Amazon because it was edited by Amazon. And also we have just launched this publication with supply chain management and logistics in Latin America. He was edited through the MIT Scale Network. So it's now I'm working in the second volume, which is associated with the papers we presented last year. And that's it. So now we have time to it's time to ask Lei to come here. So, Professor Lei Zhao, please. Claudio already introduced it. Lei, that he got his PhD in Arizona, and he's an associate professor at Tsinghua University. He has a lot of very important collaborations with top researchers in our logistics and freight transportation area. And, well, it's a very long curriculum, so I will not speak everything here. Otherwise, it will be something like 10 minutes. Okay? So, Lei, thank you so much for coming here, and please be our guest, and thank you. You can use this or here.
Wait, hello? Yeah, I can do it here. Okay, so first I would like to thank Professor Hugo, Professor Claudio to invite me here to share about the research we have done in China and in collaboration with researchers in the US and Europe. This is my first time to Latin America, but based on the tour I was with Professor Daniel, I discovered that Sao Paulo and Beijing share many commonality, so which is surprising to me because I'm here, so I can see what's going on. And in this talk, I will tell you a little bit about what's happening in Beijing. So where are these? So these are the motivation of some of the research we have been doing. So this is actually this title of the talk is the title of my PhD student's dissertation. He just graduated last July and joined a Chinese express delivery company called SF Express. I'm not sure whether you have heard of the name, but in China it's very famous. It's kind of like a #1 express delivery company, and their goal is to become a Chinese FedEx. But their service in China is actually better than FedEx. So they normally offer like a delivery within 24 hours within entire China, and with a very cheap price. But my experience with the FedEx in the U.S. is normally very expensive, not necessarily within 24 hours. But anyway, so this is based on the work. We have optimization and some learning elements in the research. So, of course, our study mostly were motivated by our observations in Beijing. So urbanization is a global trend, clearly. And so we have seen like now we have more than half of the population living in the city. And this is going to grow more, like 2/3 of the population will live in the city. And if you look at the statistic in developed country like Europe and North America, this trend has been slowing down very quickly. They became stable. But in emerging economy, I think like China, Brazil, the urbanization trend is more clear. And so the mega city, by definition, is like with a population more than 10 million population within one city. So nowadays we already have 28, but this is expected to become like more than 40 mega city. So I talk about Sao Paulo and Beijing. So yesterday, Professor Hugo asked me about some statistics about Beijing. So this is the chapter 3, and this is the chapter about Sao Paulo. So so basically, based on the population, we have a similar size. But based on the density, Beijing is less than Sao Paulo. And if we look at the income, per capita, Beijing is almost like a half of Sao Paulo. So this is the rough idea. And I noticed that during yesterday and today, Sao Paulo, maybe because of the river and the mountain, so the roads are not straight. But Beijing, because we used to have this Empire Palace, the Forbidden City. So Beijing, the majority of the city, we have this Manhattan Straits. So north, south, east, west. So and we are so this is the core area of Beijing, and then we develop a second ring, third ring, fifth ring, sixth ring. So when the city is expanding. So this is some idea of Beijing. And Tsinghua University is a little bit outside of the fourth ring. And the next big trend is e-commerce, which is clear also global-wise. And this is the development of e-commerce in the world. It remain double-digit growth. And in China is even faster. So in 2015, China already surpassed the United States, becomes the #1 largest market in the world. And this is the growth rate of e-commerce in China. So the B2C e-commerce in 2016 is like 40% growth. So it's grow very fast. And because of the rapid growth of e-commerce, so we have a lot of package, express delivery package. And as I mentioned that due to companies like SF Express and JD.com is the competitor of Amazon in China. So to give you some idea of the Amazon's competition in China, so the market share of Amazon, so Amazon has 16 markets in the world. Normally they are #1 or #2 in Germany, in UK, or in the United States for sure. Japan #2. But in China, Amazon's market share of e-commerce is 1%. And JD.com is like 36%. And the largest one is Alibaba, is like eBay in China. They have roughly 50%. So Amazon has a very difficult time in China. And like JD.com, SF Express, they work extremely hard for customer satisfaction. So they offer, like JD.com in 2012, they offer Double 11 service. So the idea is if you order by 11 in the morning, they will deliver the same day. If you order by 23 in the evening, then they will deliver by 15 the next day. So it's very fast delivery. And this delivery service covers 99% of the population of China. So this is their scale. But because of this, so Chinese customers were spoiled. We became very impatient. So when you order something online, if they deliver in 2 days, you will call the customer service to complain. Why it takes you so much time? It's so slow. So this is the idea. So the delivery, so the express delivery company industry also developed very fast because of the booming of e-commerce. So this is the growth rate of this express packet, delivery package. And to have some idea, in 2016, the annual delivery is almost 2 billion package of the year. So in Beijing, and it's more than 5 million package daily. And roughly speaking, it's like a 1 square kilometer. We have more than 300 package to be delivered each day on average. So because of this, we have seen a very large scale delivery operation, and which is actually way beyond the development of a methodology of our optimization capability. So so this is the calculation up to each day and per square kilometer. So this is the delivery density, what's happening already in China. And you can see this package. Sometimes the university or some residential area, they do not allow delivery guy to go into campus, so they will put things off campus, waiting for a customer to pick up. So this is the image. So I'm going to talk about two topics related to the express delivery operations. So Yixiao Huang is, as I mentioned, is my PhD student who is now working in SF Express. And SF Express, they also strive for like operational excellence. They started a collaboration with the Georgia Tech last year, like Professor Claudio mentioned, Professor Martin Selversberg. They have a formal collaboration with the SF Express also. So this is about the design of this urban delivery system, thinking of this large-scale, high-density delivery operations. So when we talk about the urban delivery, this two-tiered system is very familiar to us. It's not a new idea. So it's already introduced almost 10 years. So the idea is, Professor Hugo mentioned that we had a collaboration with Professor Jan Fransel in the Netherlands. So in 2013, we tried to organize a workshop at Tsinghua with Professor Jan Fransel and also with Edgar Blanco. But all of a sudden, Professor Jan Fransel has some family issue. He told me he could not make it to Beijing. But he said, I'm very interested in this workshop. I want to attend the workshop remote from Europe. So I said, then I need to buy a high-quality webcam to broadcast, to have this live workshop for him. So I ordered from JD.com online. As I mentioned, I placed the order like around 9, before 10 in the morning, and then they deliver the same day. So Edgar was very much impressed. So he asked me to take several snapshots of my computer by the tracking and also the picture with the delivery guy. So these are the real tracking of the delivery on that day. So this is the city center, city distribution center of JD.com. And this is Tsinghua University. So in the first echelon or first tier delivery, normally they have a truck or a van to deliver mostly to this satellite station for last mile distribution. So this is by truck. And in the last mile, they normally use e-tricycler, small vehicle, to deliver for the last mile. So this is the typical two-tier delivery system. In the paper by Theo Krenek in Canada, it's called a two-tiered urban delivery system. But later on, it's called a two-echelon vehicle routing problem. In recent years, this 2E VRP is mentioned more than two-tiered system. And in the majority of the 2E VRP literature, the idea is if we have a CDC here, we have several satellite stations, and the deliver in every morning. So you have the package to be delivered to the city, and you will decide which package, which depot satellite you're going to go from the CDC. And then in 2E VRP, we want to, we do optimization. So for example, for this customer, you can go to this depot, this satellite station, or that satellite station, depending on that day, which one is more economical. And, but you can imagine in the very early morning, you need to solve a very challenging optimization problem. And then in very short time, and you need to decide even at the city center which truck the package should go. Because this truck go to that satellite station, the other truck go to that satellite station. So that's very challenging and it's difficult in the morning. Because these two optimization problems are coupled together. Or vehicle routing problem, single echelon is already very difficult. But if you mix these two, it's almost impossible if you think about large scale. And if you look into the literature, so the basic, roughly, the state of the art for now, for exact algorithm, we can only solve like 100 points. And for meta-heuristic, you can solve up to 200 points. Okay, so for the 2E VRP. So, but as I mentioned, per square kilometer, we already have more than 300 customer, or more than 300 package. So what can you do? So we look at what industry people do. Like Professor Warren Paul at Princeton 10 years ago, when I first started working in academia, he always told me one thing. He said, when you are dealing with a very difficult optimization problem, you should stop and think about how people are doing this now. So because it's not like the case if you don't have a good model, people stop this industry. People are already doing a good job there. So we look at, this is a branch of DHL in Europe, like Hamburg. They split the city, partition the city into regions. So instead of having the flexibility for that customer to be served by that satellite or that satellite, they actually partition the city into regions. And they don't do optimization in the very early morning. Depending on the customer's location, if the customer belongs to this region, it just goes through that satellite station. So there's no optimization here. The optimization, like the design, will be decided beforehand. It will remain stable for a while. So this is the region. We call it a constrained delivery system because it doesn't have the flexibility as a 2E VRP. And in China, some company goes more extreme. They further partition the region into so-called cell. And each cell, in the extreme case, they only assign one delivery guy per cell. So that makes the all package dispatching even at the last mile easy. So they just, once the customer is within this in this cell, they just give it to the delivery guy. And sometimes in the last mile, they have the flexibility to negotiate among the couriers. So they say, today I have too many packages in my cell. Can you help me a little bit more? So this can totally rely on the last mile personnel to do the adjustment. So this is the idea of what's going on here. And so we have, based on this projection, from the theoretical point of view, both constraint strategy are not optimal compared to 2E VRP because you have more constraints. But the question is, we think if the density goes up, increase to very dense region, the sub-optimality of this constrained strategy may be not so serious. They may become very close to the optimal solution in terms of delivery cost or whatever. So this is the motivation of the study. And further, the idea of a cell, as we mentioned, is a little bit too strict because it has one delivery guy per cell. And so we think about if we offer a little bit more flexibility. So we merge some cells in like 2 or 3 cells into blocks. And within each block, we have 3 delivery guys they can share, 3 to 5. And that will operationally still remain the simplicity, but we have a little bit more flexibility. For optimization perspective, it's better. So we want to study the benefit of this little flexibility. And the design of the block, so the idea is how do we merge, which cells we merge into a block. So we want to minimize the total number of blocks subject to the capacity of the block. For example, if we assign 3 delivery guys in each block, then this Q bar is the 3 times of the vehicle capacity of each driver. So we respect this capacity constraint, and then we do the assignment like partitioning. And but we need to make sure the cells within the block are connected. So we borrow the idea of a multi-commodity flow. So we make sure the cells are connected within the block. So this is the model to design the blocks. But then we discover that by solving this problem, we have multiple optimal solutions. So then we do it hierarchically. So the first decision is we want to minimize the number of blocks. And the second tier hierarchical decision is we want to minimize the approximate travel distance based on each design of the block. So the approximation is from the block center to from the satellite station to each block center, and then the rough travel approximation within the block. So this is the block design. And we try to numerically study the impact of this. So this is the map of Beijing. When you look at here, so this is part of the 4 regions of Beijing. And this is the 4 region. And this is a small corner like this. So at the beginning of the study, we have a similar region design of Amazon in Amazon China. But we're not allowed to use that. So we borrow the design of this Beijing Bureau of Urban Planning. So by doing that, we respect the geographic barrier, the demographic consideration, and also the administrative consideration. So basically we use their public design, not for logistic purpose, but we have similar considerations. So we use that in our experiment. And we studied the different density. So this row is like the delivery units per cell. So it's not the delivery package per cell, it's the delivery unit. So the idea is sometimes, for example, if they deliver to the engineering college in the University of Sao Paulo, they may not differentiate by which room. They may deliver to this building. So we have this idea of a delivery unit. Of course, this is also constrained by the problem we can solve in the large scale. So from 5 to 30, the delivery unit for each cell. And when row equal to 5, it's roughly 200 package equivalent to 200 package per square kilometer. And 30 when rho equal to 30 is roughly 1,100 packages. So remember this is the number of Beijing, this is the Shanghai. So we want to mimic closely enough to what's happening now. And this is the points of rho equal to 30, this is rho equal to 5. And we try to solve the unconstrained, the 2E VRP. And the code is shared by Martin's former PhD student. This is in academia, we admit this is the state-of-the-art algorithm that can solve large-scale 2E vehicle routing problem. So this one represents how many 2E VRP instances we need to solve for each of them. This is the size of the customer points. So you can see that they can solve to 2,000 points. So this is a pretty capable solver algorithm already. But when we partition the area into regions, then we have 4 regions. So we need to solve 4 separate vehicle routing problems. But if we further partition into 87 cells, so we do not have any dispatching problem. We just, within each cell, we just solve a TSP. So this is the problem size. And we know that this is the easiest, this is the difficult. And we cannot solve when rho equal to 30, the 2E VRP algorithm cannot solve it. And up to rho equal to 25, it takes 16 hours to solve one instance. So this is and we look at when rho equal to 25, approaching, because when rho equal to 30, we do not have benchmark. So this is the ratio of each of these constrained strategy compared with the unconstrained strategy. So we can see when rho is worse than the optimal solution. So from the optimization perspective in the large scale is relatively okay. But of course, when the density is low, the cell strategy is not performing so well. And we have an additional surprise. So we look at, because we randomly generate instances. So someday you have more deliver, someday you have less deliver in different cells. So we look at the number of customers visited, and we look at the standard deviation, the variation among these replications. And we can see that, so this is cell, and the left part is the region, and the block is somewhere in between. Okay, so we see, of course, when the density is high, and if you restrict to cells, you will see a huge imbalance in workload. And when the density is very low, imagine if we have the experience of solving vehicle routing problem to optimality. Sometimes if you look at the route, you will see a very long route and a very short route. So this is what's happening. So if you offer a lot of flexibility for vehicle routing problem, you can result in this imbalance. So this is the number of customers. And if you look at the measure by the travel distance of each vehicle, and you will see that this black bar, which is the block, no matter the density is low or high, is better than either of these. So this is at the beginning of the research, we didn't expect that. But when we look at this result, we were surprised. So basically, this little flexibility can offer a significant cost benefit when the density is high. So good enough, but it additionally offers workload balance. So. And in the paper, we also did some worst-case analysis, which is to the other extreme. So meaning, what is the highest ratio when we do this restricted versus the unrestricted. And we can see that the ratio is very high. So meaning when the density is very low, you need to solve the 2E VRP to optimality. So the constraint strategy will not work. So this is the theoretical look at the other extreme. So to summarize this work, so basically we conjectured that when the customer density, the delivery density is high, the constraint strategy may not be that bad. So they offer operational simplicity, and their economic measure is not that bad. And they offer this additional, with a little bit of operational flexibility, we can enjoy certain level of workload balance. And in our another research, we studied on workload balance, because for the delivery people, they earn their income by piecework. I think this is also true here. So the more package you deliver, the more money you make. So the satellite station manager, if they dispatch the work unevenly, it will resolve big gap of the delivery personnel, the couriers. If the imbalance is huge, they are not happy. So workload balance is also important, although optimization perspective is not so easy, but it is an important measure. And of course, we did some theoretical study on the worst case result. So this is our first work about the design. So this paper, we think, is we promote the idea of properly design of the city. How do you partition the city into regions? How do you design blocks? May have more influence in the striving to develop very complicated algorithm, because algorithm dealing with this large-scale problem, we are behind. So maybe if you design the city better or worse, the result is more significant than the actual last-mile optimization. So the second work is also related to the constraint strategy. So this is kind of like a tactical, also a tactical strategy. So like a fleet allocation. So the abstract version of the problem is very simple. If you have R regions, so if you recognize the 4 regions we used in the previous study is this one, this one, this one, this one. So these are the 4 regions of Beijing. And in Beijing, the green one are not delivery region, they are parks, so not for delivery. So if we count others, it's kind of like roughly 22, 23 delivery regions. And so if we have 20 regions, if we have 200 vehicles, how do you allocate these vehicles into each region? And the idea is once you allocate the vehicle into the regions, you don't change that very frequently. You don't change that on each day. Normally it will remain stable for several months, as long as the delivery pattern is stable. And because for the human resource management, for the stability, the drivers need to be familiarized with the region. So you don't change that allocation frequently. So this is kind of like a midterm, like a tactical decision. But when you allocate the vehicles into regions, this is not a deterministic problem in a sense. The delivery on each day are different. So today is a realization like this, tomorrow is a realization like that. So the allocation is to minimize the expected delivery cost. It's not a deterministic problem. But so practical wisdom can be, so we ask the question, if the practitioner, they do not learn optimization models, stochastic programming for sure, how are they doing that? So the conventional wisdom is let's look at the expected delivery, the demand of the last year. So we will allocate the vehicle based on the expected demand or based on the expected number of customers. And then we allocate the vehicle proportionally to the expected demand or expected number of customers. So we will compare, see if you do that, whether it's good or good enough, or is there anything not so good. So by saying that, the city, I think almost every city in the world has this characteristic. The regions vary. You may have some more crowded region. You may have a more sparse region. You may have a region mostly for business. You may have a region mostly for residential area. So the regions are different. So the regional characteristic, like the customer density, the customer density can be taken care by this. Expected demand or expected number of customer. But what about the topology? Whether you have a business customer, you have a residential customer. I don't know about in Brazil, but in China, the delivery guy, they want to deliver to business, to companies. Because if the customer is not there, they can deliver to the front desk. Because in China, not like in the United States, every delivery has to be attended delivery. There must be somebody sign to receive the package. It's not like in the US, you can drop it in front of the house. It's not happening in China. So you need to assign, somebody sign it. And 5 or 6 years ago, like Amazon has this statistic, we call it the failure rate of the first delivery attempt. Meaning the delivery guy reached the customer's door, the customer is not there, you need to visit again and again. So the failure rate of the first delivery attempt a couple of years ago is like 40%. Meaning almost 40% of the delivery you need to come back again. But nowadays, both customer and the delivery guy, we try to avoid that. So now we normally pay in advance. So you don't have to wait for the customer to pay. And also we have a lot of last mile, the last 10 meter, 100 meter pickup location, like front desk or small nano stores to receive the package on behalf of the customer. So that reduce significantly the failure rate. But anyway, so the residential customer, you have a more higher failure rate. But if you go to a commercial like company or university, normally you have this like a Tsinghua campus. Daniel will see our receiving room they have a small warehouse like a FedEx pickup location because many people order online, so they help us to receive the package. So customer type, customer topology differ in regions. So mathematically, we have randomness of customer location and quantity. And we want to allocate this M vehicle to our regions to minimize the expected operational cost. So, and if we write the model, so we have M vehicle XR represent the number of vehicle allocated to region R. The mathematical expression is easy. So you just allocate the vehicle to the regions to minimize the expected cost. But the only thing is this function is unknown. We don't know. If we want to know this function, basically we need to know for each possible allocation. And we need to solve a large sample to evaluate the expected cost function. So as long as we know this function, the problem is easy. But how do we know this function? We need to learn. And this is the we want to address. And illustration. So if you look at this, I have a summation over R. So meaning each region, I assume I have a cost function, expected cost function. If region R and region R prime, assuming these are the true function, we know. We already know this. And these are the regions, these are the numbers. So each dot represents a allocated number of vehicle to the region. So we can allocate 1 vehicle, 2 vehicles, 3 vehicles to region 1, and to region R, to region R prime. So once we know each point, then this problem is easy. And in fact, we were challenged by Professor Warren Paul. He said, why do you study this? 4 region, 20 vehicle, it's just 80 points. You just evaluate this 80 points. Why you study on this? Actually, we spent 5 years, more than 5 years on this problem. So why do you bother? So the idea is to evaluate each point is expensive. So the problem I describe is an abstract version, easier version. But in reality, you may not even to have a model for the last mile delivery. You may collect the cost function, the cost, not function, each day in the field. So the evaluation is expensive. And another consideration is we call it optimal learning. So it's different from the statistical learning. The idea is, so looking at, so if this is the solution, so the summation of these green dots equal to big M, the total number of vehicles. And we have another solution. And these two solutions only differ at these 2 regions. All the other regions are the same. And so if we know the true curve, it's easy to tell the purple one is better than the green one, the solution. So the idea is we do not need to learn the curve accurately. We only need to learn the critical part of the curve good enough. So we do not want to, so in the learning perspective, we use MSE like a standard error, the mean standard error. We want to learn the curve as accurate as possible. For us, we do not want to do that. For example, if you have a curve like this, you have a curve like this. Or if you have a curve like this, you have a curve like this. Which one is better? From the learning perspective, this is worse, right? Because they are far away. But from the optimization perspective, as long as they have the same trade-off, we don't care about the gap. We care about the change. So this is the difference. So by this example, we think, so we only need to learn the critical points, a portion of the curve that affect the trade-off between regions. So and also we do not, many learning algorithms develop this asymptotic convergence. So meaning when you have infinite sample, the learning algorithm will converge to the true curve. But no company can afford infinite sample, especially when the sample is expensive. So we look at what's happening in the finite sample. So if you only have an information collection budget of N, for example, 30, 1 month, or 60, 2 months, you can only collect data in 2 months, and then you need to make a decision, what's happening. So the research question is, if we have a budget on that, how to optimally distribute the collection, information collection effort, which region vehicle combination you want to learn. You want to get a cost sample. And then so that we have a good knowledge of this true curve, but eventually we want to allocate the resource optimally or good enough. And we use this sequential information collection, meaning, for example, if I already collect information for 10 days, what should I do next to better learn And I have 11 days. What should I do in the 12th day? So this is the sequential learning. And also, in each region, we have this non-monotonicity property, meaning the more vehicle you have, you cannot be worse. But you may ask about this fixed investment. But remember, in the city, the total number of vehicles are the same. We keep the total the same. So if you sum over all the allocation of the city, it's a constant. Okay, so we have this monotonicity. So the question is whether the monotonicity help us to learn more quickly. And so this optimal learning is the concept introduced by Professor Warren Paul and his research group. And based on optimal learning, it has something called knowledge gradient with a discrete prior. The idea of a discrete prior is within each region, we have a cost curve. We don't know what is the shape of the curve. But the manager may have some experience. You may ask the manager, what will be the curve look like in your region? And the manager may draw some curve, or based on some past performance. So we may have some curve. And in this so-called KGDP, knowledge gradient with the discrete priors, we assume there is a candidate set of curves. And one of these is the true curve. The true curve must be included in the candidate set. So this is the assumption. Okay. But later we will relax that assumption because this is a very restricted assumption. And so the learning process is like on day n, the nth iteration, you decide to learn region R, M vehicle. So what if I assign M vehicle to region R? What is the cost? So in reality, you may just observe M vehicle in region R, what's happening, what's really happening, what is the real cost of the day. Or we can do it by simulation, by solving a vehicle routing problem for that particular region, given the generated customer instances. So we observe this cost, and we can update the probability of each of these curves to be the true curve. Because if we have a sample here, then perhaps this curve is closer to the sample. So this is the learning. We learn the probability of each candidate curve to be the true curve. And then we decide, what should I do next? Where I should go to collect the information. And the next day, you go there, you connect more information, you update the curve. So this is the sequential iterative learning process. And we use the Bayesian update of the probability given the new observation. And we use the probability weighted curves to estimate the true curve. Ideally, only the true curve has 100% probability, all the other curve have 0%. But this is not going to happen in reality. So we want to learn the true curve as accurate as possible. And how do we decide where to go next? So this is the idea of a knowledge gradient. So the knowledge gradient is we want to maximize the expected improvement in a measurement. So the measurement is which vehicle, region vehicle combination I want to collect the information. We call it a measurement. And the idea is pretty straightforward, so the first one, we have N. So this is our belief, the estimation based on the current observation or current belief of the probabilities of the curves. And this is what we can do based on what we have known so far. But condition on, if we study that point or that point, condition on that allocation, we have updated allocation. And we want to maximize the gap, meaning we want to find that measurement that can improve our performance the most. Am I clear? So, of course, this is a myopic improvement because we only improve the next step. We don't improve the next n step. We just, each step, we maximize that. And if I further decompose this, remember each time we only collect the cost of a vehicle allocation to one region. So meaning only the curve of one region, the probability of curves in one region change. All the other regions remain the same. So we only need to update one region. And in that one region, we need to have a probability. We need to, when we calculate expectation, we need to, for different probability, to calculate the weighted sum. And if we want to know the true expectation of what's happening next, you need to solve a lot of vehicle routing problem or collect a lot of data repetitively. This is exactly what we want to avoid. So we take an assumption. We assume the next day the cost is a normal noise around today's expected cost. So it's a normal noise. And then by doing that, we can avoid solving new vehicle routing problem. So if we partition the region into 1,000 intervals, we can avoid solving 1,000 vehicle routing problems. I hope I'm clear. But if you partition the region into 1,000 intervals, for each interval you get a new observation. We need to solve 1,000 vehicle allocation problem. Because eventually, once you know a set of curve, you need to solve the original vehicle allocation problem. So it's a computationally much more efficient, but it still needs some computational effort. So that's why this candidate set cannot be large. So in Professor Warren Paul's paper on this KGDP, the candidate set, the size is roughly 3 or 5. It's very small. And this is the pseudocode of what I just described. So as I mentioned, this candidate set is very small. And you assume the manager draw 5 curves, and the true curve has to be in these 5 curves. This is not realistic. So Warren and his PhD student relaxed this assumption. He said, what if I have a pool of curves? So the candidate set is 5. The pool of curve can be 100. So we have a larger set. And from time to time, we update the candidate set from the pool. We eliminate some curve from the set to the pool. And we add some more promising curve to the set. So they call it KGDP with resampling, meaning based on their progress of information collection with their more knowledge, they can update the candidate set. So far it's not our research, it is by Warren and his student. And because we update the candidate set, it has a superscript n, because by iteration, when you have more information, the set is updated. And H represents history, because you rely on the history of historical observation to update the set. And so basically we add one step. When the candidate, the resampling is triggered, we do the resampling procedure. And when is it triggered? So every several iteration, and also when some of the curve within the set with very low probability, like half of the curve with very low probability. So it's not helpful, you just eliminate them, you do the resampling. And this is ours. Based on the previous work, we think even you let the manager draw 100 curves or 80 curves, you assume the true curve is in the pool. It's still not realistic. So what if the manager draw all the curves not close enough without the right trade-off? So we don't assume the pool contain the true curve. And we have a regeneration because from statistical sampling we know when you have observations we can do regression. We can, based on the past experience, we can perform some regression to generate new curves. So this is the idea. And now you see the C bar, the pool also has a superscript n because we also updated the pool based on the observations. And this is the pseudocode. So we have one more step for regeneration. And when we perform the regression, the thing is we need to maintain the monotonicity. So sometimes if you update a point, you may violate the monotonicity. So the idea is you need to maintain the monotonicity, and you also want to have the curve to be smooth. If you learn about this monotonicity, many algorithms, they took the method of level off. So they average, so when they discover a point of violating the monotonicity, they just take the average of these points. But for us, we don't like it. Because when you average 3 points, they have the same value. It doesn't reflect the trade-off. Because our concern is, what if you move one vehicle to another region, from one region to another region? So we need to maintain monotonicity. At the same time, we want a smooth curve. So we use this so-called smooth asymptotic regression to perform the regeneration. And in our experiment, we did 4 regions, 20 vehicles. And from the research, we want to know how well our learning algorithm perform. So we need to know the true curve. So we solve each of these 80 points by 200 vehicle routing problem. So then actually we solve 200, 300, 400. We just want to have a good enough curve to represent the true curve. But in reality, we don't assume we can know the true curve. So, and then we randomly generate the instances. And I mentioned for each region vehicle allocation, we need to solve vehicle routing problem. But what if the vehicle assigned to the region, the demand is beyond the capacity of the vehicle? So we assume we have an additional vehicle. The additional vehicle can be the same fleet working overtime, or you really hire additional vehicle. But in either case, you have higher cost if you don't assign sufficient capacity to the region. So by doing that, we actually solve a heterogeneous vehicle routing problem with two fleet types. And this urban delivery problem, as you see, is already simplified. In reality, it can be more complicated. So the model is straightforward. We only have this additional constraint to decide whether the customer is served by regular vehicle or additional vehicle. We try to minimize. Because of the minimization, as long as the regular vehicle has sufficient capacity, we will not use the additional vehicle. And this is classical vehicle routing constraints. And we generated the instance. We did 4. So the 4 is a combination of a clustered versus random, high density versus low. So we have a low demand clustered, low demand random, high demand random, high demand clustered, 4 regions. And we want to see the result of the learning algorithm and the result of the conventional, expected demand. What is the difference? So these are some statistics of the instance we controlled. And by control the instance, we make the capacity and the demand roughly the same. So because if you have a sufficient capacity, the trade-off doesn't matter, the allocation. If you have too few capacity, the trade-off is also not so. So now we have this 100%. So meaning if you allocate properly, it will work okay. But if you move vehicle to another region improperly, then you may have trouble. So this is our control. And this is the total expected demand we generated. And how do we generate the curve? So this red dark line is the true curve we evaluated by solving 200 instances for each point. And you notice that this already costs us 1,500 hours. So just generate the true curve for 4 regions is 2 months work by this simplified problem. And our answer to Warren Paul is 80 points. If you want to do that, it's going to be a lot of time. And in fact, in the review of the paper, one reviewer said, you solve only 4 regions. The city will have more than 4 regions. Your problem setting is not realistic. I want to see what's happening if you have 20 regions. So, and we do some estimation if we want to have the true curve, because if you have 20 regions, you need to have more vehicle. So if we multiply this by 10, you will have 20 region, meaning 4 times 5. And then if we have 1,000 vehicles, now we have 20 vehicle. If we have 100 vehicle, 20 region. And the computational time to get the true curve is approximately 1 year. So in research, we cannot spend 1 year just to get the true curves. So in our experiment, we cheat a little bit. We replicate each region 5 times. So 5 regions in the group have the same true curve. But we don't let the algorithm know we actually have regions with the same curve and let the algorithm learn. So this is what we cheat. So the basic idea is computationally, this is already very expensive. If you collect the data in the field, it's much more expensive. So the brute force learning or collection is not possible. So this is the dark red true curve. What about the candidate curve? We have no idea how should we draw the candidate curve. So we randomly generate a candidate curve. I will go into that soon. So we study, so this KGDP with the resampling and the regeneration is our algorithm. We benchmark with the resampling without regeneration and some other learning algorithm. But these 3, they do not exploit the monotonicity property. They just, when they have a new observation, they update. They do not care about whether the new function is monotonic or not. And in order to generate a wide variety of curve shapes, we use this Gang-Pace function. It's a very nice function. So by modifying these parameters, so this kappa 1 control horizontally, vertically, where it converge. So by changing kappa 1, by changing kappa 2, you can move horizontally of the shape of the curve. By changing 3, you can control the convergence, the steepness of the curve, the curve. And we introduce additional 1 to make it a minimization problem, and we can control the cost. So this is we use that to generate new curves. So we choose some parameter, and then we randomly generate 80 curves in the pool. And from the 80 curves in the pool, we randomly selected 5 into the initial candidate set of 5. And initially we do not assume any knowledge, so we have an equal probability for each curve in the candidate set. And we also make sure the priors for all the algorithm are the same at the very beginning. And we do replication of 50. So for each curve, the learning, we run 50 replications to evaluate the impact. So this is the convergence curve. We set the learning is 60. Remember that if we want to evaluate the curve precisely, we have 80 points. Each point we have 200 replication. So it's a 1600, but we only do 60. We want to see if we do 60, what's happening. So this is the gap. So up to 60 points, we can reach like below 2% of optimality. But these are three that do not take advantage of the monotonicity constraint. They do not behave very well. And this random allocation is totally depending on luck. It's every day you throw a dice and decide where should I go to collect information. So it doesn't work well. And another thing I want to mention is we compare with the KGDP resampling without regeneration. They have an assumption that the true curve is contained in the pool. So meaning if the true curve is contained in the pool, is to the advantage of dash R. If the true curve is not contained in the pool, is to the advantage of our dash double R. So we look at both situations. So if the true curve is not in the pool, we see that we have a more significant gap between these two. If the true curve is in the pool, so they are very close. So meaning that if you don't have the good knowledge of the curve, the double R can have the capability to generate a curve close with a good quality. But if the true curve happen to be in the pool, we are not so worse off as comparing with the one that already assume it's in the pool. Okay, but in reality, you have no idea whether the true curve is in the pool or not. Okay, and we also compare with this heuristic. What if by expected number of customer or by expected number of demand? And we see that if we have 20 vehicles, we reduce the vehicle. We want to see if we have one less vehicle, two less vehicles, when you have more and more sparse resource, how do you which region you should reduce the vehicle? And we see that the improvement is more significant when the resource becomes more sparse. And we want to know why, how, why is this happening? So we take this 16 vehicle as an example. So this is the optimal allocation when we have 16 vehicles. So you see this both heuristic, they allocate 5, the most vehicle, into region 4. Why? Because region 4 has the highest expected number of customers. They have a high density. So they allocate more vehicle to region 4. But the optimal algorithm, based on the true curve, only allocate one vehicle to that. Because it's willing to, so if we look at this white bars, this is the additional cost, meaning penalty cost. So the optimal strategy is willing to have a lot of additional cost in region 4. And our algorithm is not exactly the same, but comparing the heuristic, we somehow catch the trend. So we are closer to the optimal allocation. And we keep going into the details. So these are the 4 regions. So this is region 4. The darker the color, the high probability of a customer location on each day. And if you look at the true curve, so we reduce from 20 vehicles to 16, meaning you need to reduce from 4 vehicles. And of course, if we know the true curve, we want to reduce the vehicles from the region with the flatter curve, right? Because the flatter the curve, the increase in cost is smaller. So if you look at among these four curves, region 4 has the flattest curve. So meaning you reduce the number of vehicles from 4 to 1, the difference is not so big. But if you reduce from these two, it's already at the turn point. You don't want to do that. So this is the optimal solution based on the regional characteristic. And this is one of the 50 generated curves. So we see, although region 4 has high density, but they are clustered. So meaning if you have additional vehicle to serve those unserved customer because they are close to each other. So the travel, because we use travel distance as an operational cost, as an objective function. So the additional cost is not that high. But if you reduce, like here, then basically the additional vehicle need to travel a lot. Okay. And so this is further to look at the unserved customer and the utilization of the regular vehicle. So we see that in both measures, the performance of our learning algorithm is closer to the optimal strategy. So to summarize, so basically we in the original version of the paper, we say we were the first to introduce learning in transportation problem. And the reviewer doesn't like it, so we don't claim we're the first, but we say we somehow study learning issues in transportation problem, and or KGDP with the resampling and regeneration algorithm, we exploit the monotonicity, and we have a smallest optimality gap against this benchmark, especially with the one without regeneration. And we somehow is able to, comparing with the conventional wisdom, we somehow can learn the characteristics of the region. I think if you have a more realistic simulation model to represent the real cost, the learning algorithm will be better off. Okay. And the advantage, so when you have a more, the ratio, when the resource is more sparse, the significance is more. So this is these two talks. Thank you very much.
Yes. Well, thank you very much, Lei. It's a really very interesting research. Very interesting indeed, and a lot of work on that. Yeah, many. Well, and now we have time for a few questions on any issue that was presented today, and I will ask you to make your questions in English so Professor Lei could answer that. Chris and Albert have microphones. Remember that we are being transmitted through the internet, through IP, TV from USP, so speak in your microphone. So, any questions?
Hi, thanks a lot for the talk. Congrats on the work. So on the second work, the prior around one of the important priors was around cost of information collection, right? Can you go a bit deeper on your understanding of costs of information collection from the perspective of the problem?
Okay.
I'm Diego. I'm from the industry, a logistics startup, actually.
Okay. In this research, we did not assume any prior knowledge. So basically, we just randomly generate curves. But in reality, I think if you do have a good curves in the initial prior, it will converge to the optimal or near optimal solutions more quickly. Yeah, so in this research, we did not assume any prior.
Sorry, maybe I didn't put myself right.
Okay.
But you mentioned the cost of information collection as a significant problem, right?
Oh, okay.
And that you want to shortcut through. And I wanted to get your ideas of your understanding of what these costs actually are.
I see. Okay. So in this study, we just assume the cost. We solve this vehicle routing problem. For example, if I assign 5 vehicles in region 4, and we just randomly generate the location and the delivery quantity within the region, and we solve a vehicle routing problem. So we use that as a simulator. And in fact, in reality, you can do more sophisticated model, even without not necessarily a optimization model. You can have a simulation model just to simulate the cost. Or possibly you can just happen if you have 5 vehicles running in the region on a day. And after the day, you just have the real cost. It's a black box. You do not need to have any model. You just collect that cost. And in fact, this research was motivated in 2007, more than 10 years ago. At that time, express delivery company, a Chinese company, they have this problem. They have in Beijing roughly 20 regions, and they have a fleet, more complicated fleet. They have vans, like trucks, and e-tricycle. So they already have a mixed fleet, and they want to decide how should I allocate this fleet into the region of Beijing. And honestly, at that time, I did not have this answer. So I left that question unsolved for almost 5 or 6 years. And then one of my master students, in one summer, he said, I have nothing to do. So what about if you give me a problem to work on? So then I say, this is the problem. That was in my mind for many years. How about you work on this? And he said, can you give me a more difficult problem? Because this sounds so easy. So I said, actually, I want you to start from an easier version. You do not consider both van and tricycle, e-tricycle. You just think about homogeneous, just one type of vehicle, and to solve it. So the student took it away, and thinking he could be able to solve it within a couple of weeks. But until he graduated and he joined IBM China Research, he didn't solve this problem, but he has the initial version. And then another PhD student continued. I said, this is a halfly solved problem, so let's continue. It took us another 5 years on this problem. So I think a short answer to you now is this is a very first step. So the idea of information collection, I think in reality, no matter by simulation or by field data collection, is expensive. Either way is expensive. But the good evaluation of the cost trade-off is important. How do we take advantage of this experience and some learning mechanism? So by doing that, so this algorithm does not rely on how do you collect the data. It can be whatever way. But there is one thing I want to mention. If you collect the information in real time, you don't, in this paper, we only collect one region at once. One region. But in reality, you collect a allocation of multiple regions on each day, meaning your information collection is more efficient than our algorithm. But so far, we have not solved a problem. The knowledge gradient calculation is not good. We tried the online version. What I presented here is the offline version, meaning we collect the information by simulation, just one region at a time. But if we collect information on the combination of regions, our algorithm does not perform so well. So I think that is a critical question. If we do online information collection in the field, that's unsolved yet.
Good afternoon. My name is Felipe. I'm from a consulting firm that oversees logistics. You mentioned that operational flexibility is mandatory to achieve workload balance. My understanding is most Brazilian companies, they lack such operational flexibility, mainly because line haul and last mile routes are fixed or predetermined. And the reason is they lack, how can I say, they lack infrastructure and technology automation. So in your opinion, what is the level of automation, infrastructure, and technology required to achieve such operational flexibility?
Okay. So I think for line haul transportation, normally the routes are fixed. They do not change frequently. But for last mile, I think because of the high level of uncertainty. So for example, today I order something, but tomorrow I may not order something. So the route can be quite different on each particular day. And nowadays, I think normally we don't do optimization by algorithm, but we rely on optimization in the mind of a delivery personnel. So in each morning when they say, these are the addresses I want to deliver, and he will solve a kind of optimization problem by heuristic or whatever in their mind. And normally they can outperform our computer because they can consider many factors we don't. Speaking of like JD.com, they can do delivery very efficiently because they have the courier, the delivery guy, very fixed within the region. They sometimes even know this couple have a fight today. So because they are so familiar with the region. But in recent 2 years, we strive for precise delivery. So in the past, they try to deliver as fast as possible. But now they offer like a 2-hour time window or even 1-hour time window. That creates a lot of trouble for the delivery guy. So meaning if they have a spatial distribution, their heuristic work pretty good. But now if you have a time window, so although these two customers are close spatially, but their time window differ. So the human to handle this two-dimensional space and time heuristically is challenging. So now like JD.com, they try to develop some automated delivery sequence to help the delivery guy. And I personally also had the experience. If you order something at JD.com, they have no problem deliver earlier than your time window. But the problem is, if you deliver earlier, I'm still not at home. So I want you to deliver within this time window. So they normally have trouble with that. But as you said, I think if you want to do this large-scale good optimization, it's very challenging. You need a digital map, you need a computing power, you need a real-time optimization algorithm. So there are many challenges.
Well, we have time for
Hello, congratulations. My name is Rogério. I'm from the real estate market. I graduated here 17 years ago. I've been investing in the real estate market in several companies. I think, how do you relate this to the real estate market? Because the real estate gives you another boundaries that complicates the model even more, because most of the times you figure out that you're going to need satellite distribution centers or any facilities that it's impossible to develop there. So probably if you run models in Manhattan, probably you're going to figure out that you need a satellite distribution center in Park Avenue, and you're never going to have that. So how do you relate this, and how do you think about how this real estate relates to the distribution model that you presented?
Okay. Yes, I think this is a very relevant question. In fact, when we in our first study, there are some research work on the partition of the region. How to partition the region so that to improve balance of the region and minimize the overall cost. But in some of this theoretical work, they assume, for example, uniform or known distribution of the location, but they do not have any restriction on the boundary of the regions. So which we think is not realistic. Because, for example, we may have a river. If the customer on two sides, different sides of the river, it matters. Or we may have a freeway. So that's why in that study we don't have we use the public distriction, because we think the design of the regioning depends on a lot of factors like this: geographic, demographic, and also, like you said, the real estate. Like, for example, like JD.com and Amazon China and SF Express, sometimes they are forced to move away from one location because the rent may increase or the landlord may not allow them to do that. So they encounter this problem. So they change their regioning or the location of the satellite based on the change of the demand pattern or based on some external factors. So they do that pretty frequently. What I heard from them is that every 2 or 3 months they may be forced to move, to change. Or if normally in one satellite station, they try to maintain the workforce not so large. Like whenever a demand of a region of a satellite require them to have more than 20 delivery guys, they will split the region. But when they split the satellite, they need to find a new location. And then they need to consider the real estate factors, as you said. But I think our work, the idea is if you have a methodology to better evaluate the candidate locations, that may be helpful to them. And I think for companies like JD.com, they have 120,000 delivery guys. So it's an army. So I think if you can...
And how many satellites?
Sorry?
And how many satellites?
Satellites, I don't have the exact number. I think in Beijing, Amazon has less than 20. And they said JD is like 4 or 5 times more than theirs. So it's kind of like 100 or something. But it's pretty dynamic. So I think if you have this huge team to actively collect cost information, if you don't use that, it's a waste. If you just have this information available, you can dig the value with the proper modeling. It can be helpful.
Thank you.
Hello, good afternoon. My name is Cynthia. I work for a consulting firm, and I would like to ask you how did and how does regulation, especially in mega cities, play a role in this kind of optimization problem? I mean, I know there are some regulations like for number of vehicles in some areas, and I would like to know how does regulation play this role in these problems?
Okay. So speaking of this last mile delivery, or sometimes we call it the last 100-meter delivery, it's in a small satellite. We did have some more strict regulation. For example, in the city of Beijing, the e-tricycle, they don't have an official license plate, only like a vehicle, like cars. We have a license plate. But over time, they see more accident because of this e-tricycler. So nowadays, I think starting from 2 years ago, they require each company, they use their e-tricycle with their logo, with the unified design, and also a license plate. So in that case, whenever something bad happens, the traffic police know which company does this guy belongs to, and also by the number, they can track which is the delivery person. So this is kind of the regulation on the delivery of e-tricycler. But the traffic rule, I think, is similar to here. Yesterday, I saw on the street, the e-tricycler or motorcycler, they do not respect any traffic rule. So red light, emergency road, whatever. So for us, if we drive on the street, we need to be very careful to them, because they drive very fast, and it's very quiet. Normally, for example, e-bicycle, there is a speed limit of 25 kilometers per hour by production regulation. But when they sell the bicycle to the customer, they turn off that regulation, meaning the e-bicycle can go much faster, like 40 kilometers per hour for a bicycle. So sometimes it causes accidents. Yeah, so from the optimization perspective, as I said yesterday, their travel distance can be approximated as a deterministic, because the congestion, traffic lights, nothing affect them. They just move around. Yeah.
Hi, my name is Vinicius. I'm from a Escola here called Senai, and I think at São Paulo, I think the true cost function varies along the time, very frequently. You have some things like a few months ago, a road collapsed, and I think that if you think about the true cost function, they change a lot along the time, very frankly. How to deal with this?
Yes. In the current work I just presented, we assume static market or condition for a period of time. But in fact, Professor Warren Paul, throughout these years, he said offline problem is not so interesting. The interesting problem is online learning. So meaning, even though after you already assign the resource, you still keep collecting the data. And then you may be able to discover a change in the demand pattern. Even without, I think for the reconstruction of some road, you already know what's happening. But the change of demand pattern, sometimes you cannot observe. So his idea is if you have this online learning, so you keep collecting cost, you may be able to identify that. But yeah.
So good, thank you.
My name is Carlos. Again, sorry, thank you very much for your presentation. My name is Carlos Nogueira. I'm also a consultant. And my question is a little outside of the study. And you touched it in one of the answers before. How much do you realize, if there is any, kind of concern generally in the community by the safety of those guys doing this last mile delivery? Because I think as the speed expectation to things get fast at home, this market or the presence of those delivery guys get bigger and bigger and bigger. And how do you perceive this as a concern about safety? I'd like the guy that brings my thing goes to his home safe at the end of the day as well. So do you perceive any kind of concern raising in China about this, or in Beijing?
Yes, we did. I saw yesterday here you have a Logi, you have iFood, Uber Eats, and I mentioned initially Daniel said this is very special, and then I said we have a similar thing in Beijing, and the largest company in Beijing called Meituan Delivery for meal delivery. They in October of 2018, last year, they have a daily order of 20 million orders, so in a day. So it's a huge market, and there are several issues related to this. The advantage is convenience, as you said. So the other factor is safety, safety on the street, like accidents, and the safety at home. For example, we may be worried about what if the guy so familiar with this region, he may break in during the daytime. So we do have this concern. Like me, if I order delivery in the office, I tell them the room number, so they deliver to my office. If I order delivery to my house, I only tell them the building number. So I said, when you arrive downstairs, call me. I will go to pick it up by myself. So I never tell them my apartment number. So this is the way I try to somehow protect against the freelancer. But for JD.com, the B2C delivery, normally their workforce are very stable. And sometimes I ask them to deliver water, bottled water, heavy stuff. I'm lazy. So I tell them my apartment number. Somehow I trust the guy, because this guy to deliver to my apartment in the past 3 years is always this guy. So it's as you said, it's a trade-off between convenience and safety and security. And another thing for this meal delivery is the environmental issues. Think about 20 million meals per day. That will result in 20 million food package per day. So whenever they deliver, they assume you need the chopsticks. So they always give us extra, more than enough chopsticks. But we eat at home. So I said we put no chopsticks. But they still give us chopsticks. So on the day before I came here, my wife put no chopsticks 10 times. And then finally, they did not give us chopsticks. Yeah, so this is the environmental issue. And some companies, they already learned, they use a paper box instead of a plastical box. They use so sometimes they try to reduce the impact to environment. But I think based on our observation, at least in Beijing, convenience is very important, so we are somehow willing to sacrifice other issues. So for me, sometimes when I go back home very late, I don't want to cook. So I have estimation I may arrive at home in 30 minutes. So before I depart from my office, I order some meal. And roughly after I arrive, the meal delivered, then I can have a meal. So by doing that, we sacrifice other issues.
Really? May I? Sorry, I am Sueli from T-Systems, Deutsche Telekom Group, work for HP RFID Center of Excellence. And I apologize if my question is going to be some repetitive one, but you mentioned that Amazon faced some issues and was very surprised because they invest a lot in technology, drones. What's the problem? They don't know the region very well. What's wrong? And in this particular, when you mentioned that they faced some issues, what was the particular problem? They didn't have people that could understand how to deal with the region.
Yeah, in fact, I have a pretty close collaboration with Amazon China. Some of our students, they're working in the Amazon China Last Mile Delivery team. They call it AMZL, Amazon Last Mile. I think their trouble is first, they're a global company. So as I mentioned, they have 16 markets worldwide, and they perform very well in other regions. For example, in India, now they put much focus in India. But in China, I think one thing is the competition from Alibaba, from JD. And they, as I mentioned, they offer better convenience than Amazon model, even in the United States. Honestly speaking, I'm from China, so whenever I go to the United States, I think their service, people say Amazon has a superior service, but I think their service, comparing with the Chinese B2C retailer, is very bad. Because we have a same-day delivery, next-day delivery, almost free. So like if you purchase more than $10 order, you get a free delivery. Even it's not free, it's $1 charge. So, and they 99% of the time, they deliver on time. Like Amazon, when I go to Informs to attend an academic conference, I use Amazon one-day delivery. But one day does not include Sunday. Sometimes does not include Tuesday, I don't understand. And even I order one-day delivery, they may be 2 days. And the delivery is actually not to my hotel room. It's to downstairs, second floor, FedEx office. And I need to pay $10 additional to pick it up for them to move from first floor to second floor per package, as long as the package is weight over more than 1 pound. So anyway, so in China, I think because this company, they compete toughly for customer convenience. But Amazon, I think they have a global market. They cannot change their global policy based on one country. That does not occupy very significance in their global market. So several years ago, Amazon China, the market share is 2.7. And when I studied in the US, I'm an Amazon customer, loyalty to Amazon. So when I went back to China, I still purchase at Amazon. But over years, I was converted to JD. So I always talk to the Amazon manager. I said, you push me away from Amazon. So I think they are frustrated. I mean, the Amazon China, because sometimes they have difficulty communicate with the headquarters about their challenges they face in China. And another thing is the website. So the website, I think Amazon globally has the similar design. But in China, other, how do I say, the B2C retailers have a different design. It's relatively easier for us to search. But Amazon doesn't change. And they know, at least Amazon China know. But they cannot change it because this design is globally. And from operational perspective, I understand. Because you are a global company, you need to have a global strategy. So I think these are the reasons I observed. Yeah.
Well, now it's 4 p.m. We're going to finish the seminar now. I want to thank you very much, Professor Lei, for sharing with us all his knowledge. Thank you, Lei. It was really great having you here at the University of São Paulo. I hope that it will be just the first time, okay? Before coming to São Paulo, Lei was in Peru with some friends in Lima. And I want also to thank all of you that came here to University of São Paulo to stay with us, and I hope that you have learned something and found something interesting in this presentation. Also to the guys there in the internet TV there. And I also want to thank very much to Alvaro and Chris and Fabiana for helping us to organize this event. And that's it. Thank you.
Yeah, thank you. Yeah, although I have just been here for a little bit more than 1 day, I did observe we have many similarity, at least in the perspective of urban logistics. So I do look forward to closer collaboration with both academia and industry. So if you happen to come to China, to Beijing, I'm happy to house you there.
Thank you, Lei.